Hello, dear students. Welcome back to our refrigeration and air conditioning subject discussion. So now let us move on to our second module, where we will be discussing another type of refrigeration process called as vapor compression refrigeration system. So let us slowly move on to our module 2 from where we stopped at module 1. So in our module 1, we considered our air refrigeration system. That is, air refrigeration system means using our atmospheric air itself as the working fluid. Okay, so when a atmospheric air is nothing but a simple gas. Okay, so when a simple gas such as atmospheric air is used as the working fluid or the refrigerant. Okay, refrigerant means the working fluid which is used in the refrigeration system. Okay, when such a gas or atmospheric air is used as the refrigerant, this will be the resulting TS diagram of that refrigeration system. So you can see 4 to 1 was our constant pressure heat absorption or the refrigeration process. 1 to 2 is our isentropic compression process. Then 2 to 3 is our constant pressure heat rejection or heat exchanger, where the heat is rejected to the surroundings. Then 3 to 4 is our isentropic expansion process. Okay, so when we consider such a case, okay, actually we considered this air refrigeration system by modifying the Carnot refrigeration cycle, because we in the module 1 we discussed that this Carnot refrigeration system the Carnot refrigeration cycle is not attainable in a practical case because of various reasons. But because this Carnot refrigeration cycle is the most efficient cycle, every attempt should be made to reproduce it with the actual equipment. Actually, the main purpose of discussing the Carnot refrigeration cycle is it is the most efficient cycle. So whenever as mechanical engineers or after the practicing engineers, whenever we design a system, for example the refrigeration system, we should try to attain the maximum possible efficiency. Okay, so every attempt should be made to reproduce this Carnot refrigeration system refrigeration cycle with actual equipment. Okay, certainly the reversible processes cannot be duplicated. Okay, but at least, so you can see the underlined line here, but at least the rectangular shape of that cycle on the temperature entropy diagram can be maintained or can be tried to be maintained. Okay, so actually when we had considered the air refrigeration system, or when the atmospheric air was considered as the working fluid, we did not get the rectangular shape on this TS diagram, on the temperature entropy diagram, but instead a quadrilateral shape was almost a parallelogram like shape was obtained here. Okay, so instead of such a parallelogram shape, suppose, okay, actually we are only supposing, suppose we were able to produce or we are able to design a system which can have at least that rectangular shape in the TS diagram, then that system would be at least similar to our Carnot refrigeration cycle. So that is the meaning of here. At least the rectangular shape of the cycle can should be maintained on the temperature diagram. So how it can be attained? If the rectangular shape is to be maintained, the heat should be received at one temperature level and rejected at the another. Okay, but in our module 1 we discussed a gas such as atmospheric air as the refrigerant or the working fluid. But when we are using a gas like atmospheric air, the cycle would be appearing like in figure 10.6, that is the above figure. Okay, this is the above figure 10.6, rather than a Carnot cycle. Actually, if our system was representing a Carnot cycle, instead of this parallelogram shape, the Carnot cycle would have got a rectangular shape like this. Okay, so how we can at least represent a rectangular shape in the TS diagram? Okay, so and the isentropic compression and expansion process are 1 to 2 and 3 to 4. then the processes 2 to 3 and 4 to 1 are the constant pressure cooling and heating processes respectively. Okay, so how this air refrigeration system is different from a Carnot refrigeration cycle. When we are considering the shape of the Carnot refrigeration cycle, which is a rectangular shape, here when we are considering air as the working fluid or simply a gas as the working fluid, additionally we are seeing that there are some additional area like this shaded area. This shaded area here, the above area is the X and the bottom area is marked as Y. This X and Y areas are here we are getting additionally or in addition to the rectangular shape of the Carnot refrigeration cycle. Actually, this areas X and Y were introduced in this TS diagram only because we choose atmospheric air or simply a gas as the working fluid. Okay, so what is the effect of this X and Y? So now let us discuss that. At point 4, the temperature must be lower than the cold room temperature so that the gas receives heat in the constant pressure process and it rises to a temperature no higher than that of the cold room. So here you can see at point 4, the refrigerant or our atmospheric air should be having a lower temperature than the cold room. Cold room is a freezer compartment or the area where we want to have our refrigeration or the area where we want to create our cooling effect. Okay, so when we are admitting our atmospheric air into that freezer compartment, the atmospheric air temperature should be lower than the cold room temperature. Then only it can absorb heat from that cold room and finally attain the temperature of the cold room. Okay, so that is why this additional area, the additional area Y is coming over here. Okay, then what about this additional area X over here? The same atmospheric air after compression process, that is 1 to 2, it is going to reject the heat to the surroundings, or the surroundings is nothing but the atmosphere. So for rejecting the heat to the atmosphere, the working fluid, which is gas or the air itself, it should be having a higher temperature than the atmosphere. Okay, so that is why T2 is greater than T3. T3 is nothing but the temperature of the surroundings or the atmosphere. So only if the gas is attaining a temperature T2 which is higher than T3, then only it can reject the heat to the surroundings or the atmospheric air or the atmosphere. Then and during this heat rejection process, finally our working fluid, which is gas or our atmospheric air itself, the air will finally attain the temperature of the surroundings. Okay, so it is simple logic. So that due to this heat rejection process by that gas, this additional area X is created over here. Okay, so what are the effects of this areas of this both of these areas X and Y? The effect of area X is to increase the work required, okay, which decreases the coefficient of performance. Okay, so this effect of area X, it increases the total work consumed and which decreases the coefficient of performance. Then what is the effect of area Y? The area Y will be increasing the work required. Again, it will increase the work required, which again reduces the amount of refrigeration. Okay, so both of these areas X and Y, it will be reducing the coefficient of performance, but it cannot be avoided because here we are using gas as the refrigerant, gas as the working fluid. Okay, so but we know the very shape of this TS diagram is different from our Carnot refrigeration cycle shape. So it is having a lesser efficiency than the Carnot cycle shape. So at least suppose we want to introduce the shape of a rectangle or the shape of the Carnot refrigeration cycle in the TS diagram. So what can be the next alternative? Okay, so now we understood that when we are using a simple gas as the refrigerant or the working fluid, the Carnot refrigeration cycle, or at least the shape of the Carnot refrigeration cycle, cannot be produced on the TS diagram. So, but at least with the but at least we should try to implement that rectangular shape of the Carnot cycle in the TS diagram. So, what we can do here, instead of a gas, a refrigerant may be used that condenses during the heat rejection process and boils during the heat addition or the refrigeration process. Okay, so if such a working fluid is possible, so you please assume that is we are using a working fluid, okay, which will boil or evaporate during the heat absorption process. So here the heat absorption process is 4-to-1 or the refrigeration step. So suppose we are using a working fluid in this refrigeration step. So it will and such a working fluid, suppose it can absorb heat and evaporate, okay, or it can change its phase from liquid to vapor. Okay, we are just assuming that. Suppose we are using such a working fluid, then what will be the shape of this 4-to-1? Instead of a curve like this, during the phase change from liquid to vapor, instead of this curved line, 4-to-1 will be a horizontal line. Okay, then suppose that working fluid can again change its phase from vapor to liquid during the heat rejection process. So here the heat rejection process is 2-to-3. So from vapor state back to liquid, or suppose the working fluid can condense during the heat rejection process, then the shape of the line 2-to-3 will no longer be a curve, but it will be a horizontal line. Okay, so because how it is becoming a horizontal line, both this 2-to-3 and 4-to-1, because whenever a material is undergoing a phase transformation, it will be happening, the phase transformation itself will be happening at a constant temperature. Okay, so instead of a simple gas like our air, which is used as a working fluid, suppose we can use a working fluid which will evaporate during the refrigeration process, and suppose it can condense during the heat rejection process, then almost a rectangular shape can be attained. Almost a rectangular shape can be attained at the refrigeration step and at the heat rejection step. So here such a shape is shown over here. This is the Carnot refrigeration cycle when a condensing and evaporating fluid is used as the refrigerant. So here this is the TS diagram for a refrigeration system where a working fluid which can evaporate during the heat absorption or refrigeration process and which can condense during the heat rejection process is used. Okay, so here we are not making any big change in our air refrigeration system, but instead of a simple gas like air, we are introducing a new working fluid which can evaporate during the heat absorption process or the refrigeration process. So 4-to-1, this working fluid will be evaporating. So that evaporation process will be a constant temperature line. So it will be a horizontal line like this 4-to-1. Then 1-to-2 will be our compression process. So you can see over here. So this is our diagram. 4-to-1 is our freezer compartment process or the refrigeration step. It will be evaporating in that the working fluid will be evaporating in that refrigerator. So it will be a horizontal line like this. Then during 1-to-2, the compressor process will be isentropic process, that is 1-to-2. Then 2-to-3, it will be the condensation process or the heat rejection process, which is happening in the heat exchanger. The condenser means the working fluid is condensing during the heat rejection process, which is nothing but 2-to-3. Then 3-to-4, final our constant entropy or isentropic expansion process, 3-to-4. Okay, So 3 to 4 it is our expansion process. Okay, so let us continue later.